Welcome back after the lunch session, lunch interval. Now, I'll give you a simple example of this difference between, look at the terms non-dimensionalization and ordering or scaling. Now, if I ask you what is the average height of participants in this workshop, let us say age average is, I'm taking a simple example, average height of participants in the workshop, this workshop. Can you give me a number? Huh? 1.62 centimeters. Okay. Now you have expressed it in centimeters, so this number looks large, 160. Now I can write it as in millimeters, it becomes even larger. Now what we are doing is an approximation. Okay, we have an equation which is difficult to solve, and we are trying to estimate whether we can neglect certain things in the equation to simplify the analysis. Now when you neglect a term, it is not the absolute value of the term itself, because that will depend on the units. This is an example. Suppose I use microns, then what will be this value? 1620, then 3 more zeros. Okay. Now if I write it in this side in meters, it is 1.62 meters, the same quantity. So this is looking like an order 1 quantity. Okay. Now if I write it in kilometers, then it is going to be 0.00162 kilometers. Okay. Now likewise, if I write it in nanometers, it will be 1.62 into 10 to the power 9 nanometers. Right. So when you are looking at a quantity and you want to say whether it's large or small, it's not the value of the quantity in dimensional form, because that depends on your choice of the units. Okay. So you have to decide what is your scale. Now I can define an average height, say H star average, as this dimensional quantity H average by some length scale. Now let us look at the value of this. Suppose I take L to be 1 centimeter. Okay, then what is H star? H star average. It is going to be 162. It is a non-dimensional number. Okay. If I take L to be 1 millimeters, then H star average will be even larger. If I take L to be 1 nanometer, my length scale, then H star average will be a huge quantity. On the other hand, if I take L to be say 1 kilometers, then the average value will be 0.00162, and if I take L to be 1 meter, then H star average is equal to 1. So all these are non-dimensional numbers, okay, but not 1, sorry, 1.62. If I ask you which one is order 1, you will say the last one. Okay, the others are huge because you have taken different scales. Now, what is the appropriate scale? Okay, so we have talked about the continuum hypothesis. So in the context of fluids, it is also valid for elastic solids and so on. So suppose I look at this tabletop over here. to your eye, it appears to be a continuous distribution of matter. Okay. So you are making the continuum hypothesis. But it is not really continuum. I mean, it is not continuous, the distribution of matter. You know that it's made up of molecules with gaps in between. So if you bring a microscope and start zooming a particular area, you will see the gaps. Okay. So if you are a physicist and you want to look at what is happening at the molecular level, then your length scale will be of the order of microns or nanometers. Okay. Now as an engineer, let us say you have a breeze blowing over the table and you want to find out, measure or compute whatever it is, the flow pattern over the table and find the drag on the table and so on. Then what is the length scale of your interest? It will be the length of one side of the table or maybe one diagonal of the table or something like that. Okay. So sometimes you have a natural scale in which you are interested in. So when you are making an approximation and you are neglecting certain terms, two things you have to keep in mind. One is it is not the absolute value of the term. Okay. So if you have an equation, you neglect one term in the equation in comparison to some other term in the equation. So you have to compare the ratio of the, look at the ratio of the forces and things like that in the equation. That is the first thing. Second thing is that here, of course, we have an equation which we have not solved. Solution is unknown. Each term in the equation has some unknown gradients and derivatives or whatever it is. You are trying to make estimates without solving. Okay. Now, if you have the right scales, then the variables will be order 1. Then at a glance you can tell what is the order of magnitude. So with this, let us go back and look at it again. For example, if you look at the momentum equation, you had rho u del u del x plus del v del u del y is equal to minus del p del x plus mu del 2u del x squared plus del 2u del y squared. This is the x momentum equation which we want to solve in dimensional form. Now, by looking at it, you are not able to tell what are the order of magnitude. So if you introduce order 1 variables, so in the boundary layer we had x star, which is x upon L, order 1. We had u star, which is u by u infinity, order 1. So how did we get this ordering? This we got from the boundary condition. We know the upstream flow is a uniform flow with flow speed u infinity. So we are saying the dimensional u is order u infinity. You anticipate that that is the maximum value. Here you have a plate of length L and x is a coordinate along the plate. So you are saying that at a typical point near the plate, x is order L, so x star is order 1. Now, in the boundary layer, we said capital Y is y by delta naught, but delta naught is the thickness of the boundary layer which is unknown. Okay. But if y is order delta naught, then capital Y is order 1. Similarly, we said let capital V be the dimensional V by some V naught, and I choose this scale so that it is order 1. So going back to this example, here this was a 1, this choice of the scale made it order 1. Okay. So now these others are arbitrary non-dimensionalization. This is a non-dimensional which has made quantities order 1. So it is the proper, because we have used the proper scale for it. Okay. So here we are saying that let us use the proper scale which is not yet known, delta naught, and this is not yet known. Okay. Now, if you look at something like say del u del x, which is there in a continuity equation, if I write it as u infinity by L del u star del x star, because u star and x star are order 1, we are claiming that this is order 1. So this quantity in front of this is telling you what is the order of magnitude of del u del x. Similarly, if I look at del v del y in dimensional form, this we are saying is V naught by delta naught into del of capital V, del of capital Y, and because this capital V is order 1, capital Y is also order 1, we are saying this is order 1. Now these two are same order of magnitude because 1 is the negative of the other from your continuity equation. So that gives you one relation that U infinity by L is V naught by delta naught, or I can write it as V naught by U infinity is delta naught by L. So we are saying that the ratio of the y velocity scale to the x velocity scale is the ratio of the y scale by y length scale by the ratio of the x length scale. The x length scale was L and the y length scale is delta naught, and we showed we are anticipating the amount less thin, so we are anticipating that this is much less than 1. Now let us look at this equation and write it in terms of the scale coordinates, and we will see the advantage of the scaling, introducing non-dimensional variables which are order 1. So this equation I will write as rho U infinity squared by L into U star del U star del X star. So this is the first term. Now what is the advantage of writing it this way? The advantage is that you are saying that U star is order 1, X is order 1, so this whole thing is order 1. So if I ask you what is the order of rho U del U del X, you will immediately say it is rho U infinity squared by L. Now if I look at the second term, I will write it as rho into V naught U infinity by delta naught into capital V del U star del capital Y, and again this is order 1. So if somebody asks you what is the order of magnitude of rho V del U del Y, you will say rho V naught U infinity by delta naught. Now, so I know the order of the two terms, and if I find that one is small compared to the other, then I can neglect it. So if I compare this with this, what can we say? The V naught by delta naught is what you have here, that is the same as U naught by L. So below this I can write it in an equivalent way. This quantity is rho U infinity by L into U infinity. Okay. So this actually is the same as this, what you have over here. That means both are same order of magnitude. Now we go to the right hand side. I'll write it below here, minus rho U infinity squared by L del B del X, del of P star del X. Okay. Now P star I forgot to define over here. P star we are defining as P by rho U infinity squared. And from Bernoulli's equation you expect this to be order 1. So, and this is your X star. So this is also order 1. So if somebody wants to estimate without solving the equation, what is del B del X? What can be the maximum value, let us say? You will say it is order of rho U infinity squared by L, which is the same as the order of these two terms on the left hand side. So this, they are same order of magnitude. Now we look at the other terms. You have this one is mu U infinity by L squared into del 2 U star del X star squared. Now once again this quantity is order 1. So the order of mu del 2 U del Y del X squared is mu infinity by L squared. At a glance you can tell. Then look at the next term. This will be mu U infinity by delta naught squared into del 2 U star del Y squared. Again the advantage of writing this is that you have used scale variables which are order 1. So we are assuming that all the gradients are order 1, all the derivatives are order 1. So if I ask you what is the order of mu del 2 U del Y squared, you will say mu U infinity by delta naught squared. So there were 1, 2, 3, 4, 5 terms in the equation. We have seen that 3 of them are same order of magnitude. Now if you look at these two and compare this with this, if you say that delta naught by L is much less than 1, then this is going to be the dominant term. This is going to be much larger than this. Okay. Because you have delta naught square in the denominator, so this is a large quantity because the denominator is small. So we argued that this term could be thrown out or neglected. So instead of solving the full equation, you solve an approximate equation where this term is neglected, not there. And if that helps in the analysis phase, then that is good for you. Okay. Now, this term, we have found these three are the same order of magnitude. This one may be much larger than this, same order of this, or much less than this. If you say this is much less than this, then your approximate equation will not have any of the viscous terms. And we have seen what happened when you neglect both the viscous terms. You get a solution which doesn't satisfy the no-slip boundary condition and gives the absurd prediction that drag is 0. So if your approximate equation which you want to solve is to reflect the physics, then at least one of the two viscous terms must be there, and you will keep the larger one. Okay. Now, if this term is the dominant term, then you will have a very simple equation where these three are also neglected. It will be simply del 2u del y square equal to 0. If you solve it, you will see that from the solution that also will not match your boundary conditions, fit your boundary conditions. So the conclusion is that this term must be same order of the other three terms which are equal. So then you will have an approximate equation where you will have this term, this term, this term, and this term, but this will be neglected. So from that you get the delta naught square. So what you will do is you will equate this term, which is mu u infinity by delta naught squared to rho u infinity squared by L. If I bring this term to this side, you have delta naught squared equal to mu by rho u infinity. If I divide by L, then you will have this, which is 1 upon RE. So our anticipation was this y length scale is much smaller than the x length scale, and you have now the condition for it. When will that happen? It will happen when the Reynolds number is very large. So we have found this estimate that delta naught by L is 1 by square root of RE, and this will be much less than 1 if RE is much greater than 1. So when that happens, then you can neglect this term in the equation. Now let us go back and complete the ordering of for the second equation. Pardon? Here your delta square by L squared is 1 by RE. So if you take the root, you get this. Alright, now let us look at the y momentum equation. So y momentum equation was rho into u del v del x plus v into del v del y equal to minus del p del y plus mu into del 2v del x squared plus del 2v del y squared. Now let me rearrange this equation and keep the del p del y term on one side. So I bring this term to the left hand side and move these two terms to the right hand side. So this will be minus rho into u del v del x plus v del v del y plus the viscous term mu del 2v del x squared plus del 2v del y squared. Now this I can write as rho u infinity squared by delta naught del p del y. and this side I can write it as minus rho u infinity V naught by L into u star del V star del x star. That's the first term. Second term will be minus rho V0 squared by delta naught, sorry, not V star, this I am using capital V notation inside the boundary layer. This will be capital V del V del Y, del capital Y. Now once again, because these are order 1 variables, this whole thing is order 1, this is also order 1. And if you continue with it, you have the viscous terms mu V naught by L squared del 2 capital V del x star squared. So this quantity is order 1. And the last term will be mu V naught by delta naught squared into del 2 capital V del y squared. Now what you can do is make this coefficient 1. So divide both sides of the equation by rho u infinity square by delta naught. This equation is still in dimensional form, although I have introduced non-dimensional variables. Okay, so you want to see what is del p del y. Okay, now you will have the ratio of this to this, this to this, this to this, and this to this. So 4 quantities. So let us find it. So if you look at this first one, so everywhere I have to multiply by delta naught by rho infinity square. This is the factor with which you will multiply each term on the right hand side. So this one will be, let's do the work here, just below this. You will have delta naught by rho u infinity squared into u infinity V naught by L. This is what you will get from the first term. Now you see that this u infinity square 1 will cancel with this. And I forgot the rho over here. There was a rho u infinity. The rho will cancel out. So you will get delta naught by L into V naught by u infinity. Delta naught by L into V naught by u infinity. Now you can go back and look at it. We had V naught by L, V naught by u infinity is equal to delta naught by L. So what you are getting here is actually delta naught by L whole square, which is a small quantity. Similarly, if I look at this second term, you are going to have rho V0 squared by delta 0 squared, and then you have to multiply by this reciprocal of this factor, which is delta naught by rho infinity squared. So once again the rho cancels out, one of this delta naught cancels out, and sorry, this was just delta naught. So delta naught just cancels out. It is V naught by infinity whole square, which is the same as delta naught by L whole square. So these two terms are same order of magnitude, and both are small because delta naught by L is small. Now let us look at this term. You have, let me use a different color, mu V naught by L squared. You will multiply it by the reciprocal of this term, which is delta naught by rho u infinity squared. So this I can rearrange this way. Let me write it as V naught by L, sorry, V naught by u infinity, that is non-dimensional, delta naught by L, and then you are going to be left with rho infinity L by mu. Let us see if it is correct. You have mu V naught delta naught, mu V naught delta naught, and you had a rho L square infinity square, 2 L's infinity square. The reason I have rearranged it in this way is that you know that V naught by L, V naught by U infinity, this non-dimensional ratio of the two scales is delta by L. So, and this is 1 by RE. So, you have 1 upon RE into delta naught by L whole square coming in. Okay. And similarly, if you look at the last quantity, you are going to have mu V naught by delta naught squared multiplied by the reciprocal of this quantity here, which is delta naught by rho E infinity squared. Now here this delta naught in the numerator will cancel with one of this, and you can write it as, let me write V naught by U infinity, and here you have mu by rho U infinity delta naught. So let us check if this is correct. You have mu V naught here, you have mu V naught, and rho infinity square delta naught, rho infinity square delta naught. But I have arranged it in such a way this is non-dimensional, this is also non-dimensional. Now this I can go further and write as V naught by U infinity mu by rho infinity L into 1 upon delta naught by L. Now V naught by U infinity is delta naught by L, so this will cancel with this, so this is 1 by RE. So the last term is 1 by RE, and we have shown that delta naught by L is 1 by root of RE, so this these terms which were order of delta naught by L squared are also order 1 by RE. So this gives you that del P del Y is order of 1 upon RE. So when RE is large, or you can say this is the order of delta naught by L whole square. So when RE is large, delta naught by L is much less than 1, this can be neglected. So that gives you the drastic approximation that del P del Y is approximately equal to 0. And just before the lunch interval, I had written down the equations, so I don't have to write it again. So these are what are called, referred to as Prandtl's boundary equations. I have written them in dimensional form. Okay. So what is the approximation? You are saying that the pressure variation in the y direction is like your hydrostatic. Simply del P del Y is 0. And in the x momentum, that del 2u del x squared term is neglected. So this actually changes the character of the equations if you have studied the classification of PDEs from elliptic to parabolic. Anyway, for the timing, let us not worry about it. Only thing we can note is that if del P del Y is 0, then means P is a function of x only. So another way to write it is replace this del P del x by dP dx, and then you don't have to write this second equation. So we can write Prandtl's boundary layer equations this way: del u del x plus del P del Y equal to 0. This is part of the system. There is no approximation in this equation. Rho u del u del x plus v del u del y is equal to, now I can write it as minus dP dx plus mu del 2u del y square. So what I have done is just a change in notation. Instead of writing del, if you write del P del x, that could be a function of x and y both. But if I write dP dx, it cannot become a function of y, because total derivative implies that P is a function of x. Then you don't have to write the other equation. So this is an equivalent form of Prandtl's boundary layer equation. Now if you solve it, you will get the solution, but the solution was matched with the approximate solution of which we found in outer region. So we have to discuss a little bit about the matching. So let us say this is your plate, and I'm going to draw now an exaggerated figure. Let us say this is the edge of the boundary layer. Now, in both the equations, so this is what we call the outer region, and this is what we call inner region. Now, in both the equations, the governing both the regions, the governing equation is the Navier-Stokes equation, which I will write as NSE. Now, we are making two different approximations. This in the outer region is being approximated by Euler's equations, and here this is being approximated by Prandtl's boundary layer equations. Why are we doing it? Because it's difficult to solve the Navier-Stokes equations. This solution we have already got for the flat plate. This also holds for other geometries, and now we have to solve this. But to solve this, we need boundary conditions. So we will insist now that there is a intermediate region or overlap region, which I am symbolically indicated this way, which includes the outer part of the inner region and the inner part of the outer region. We are going to say that in this particular region, both the approximations are going to be valid. So we are going to match the solution of the Euler's equation and the solution of the boundary equations in this region. So the solution matching will be done not at one point, but at several points, all points in this region. Now symbolically I can write, if I say look at the x component of velocity, in the outer region we had u approximately say some function u outer of x star y star, and so this we have found for the flat plate was equal to 1, but I am doing it for the general case. Now in the boundary layer, let us say this is some u inner. Now this is going to be a function of x star and capital Y. So I have used order 1 coordinates in region 1. In both the regions, x star is order 1, here y star is order 1, and here capital Y is order 1. Now what is the link between capital Y and small y? Small y is Re to the power minus half into capital Y. We have shown that thickness of the boundary layer is order Re minus half. So inside this thin layer, the small y, capital Y is order 1, so small y is order Re minus half. Okay. So if I say epsilon is 1 by Re, let us say, a small parameter, I can say that y is epsilon to the power half into capital Y inside this. And in the outer region, the small y is order 1. Now, if I have a point here, say P, in the intermediate region, what would be its value, the y coordinate? If I look at the y coordinate of, sorry, this is y star. What is the y coordinate of this if I measure it on the L? L is the length scale in the y direction for the outer region, okay, and this point is close to the wall. So yp by L is going to be much less than 1. But if I take the same y coordinate and non-dimensionalize by delta naught, this is going to be much larger than 1. So I go back to that example which I took, the average height of participants in the workshop, and somebody suggested 162 centimeters as the number. And here, as we showed you that if I take different length scales to non-dimensionalize, this value can be either order 1 or very small or very large. Okay. So here what is happening, something similar to that, there are multiple scales. So this monolayer is, this is of course an exaggerated view, is very thin. Its order is dimensional distance from the wall, order of magnitude is delta naught. So if you have a point in the outer region which is a point in the intermediate region which is outside the boundary layer, its y coordinate is going to be large compared to the boundary layer scale. Okay. But the same y coordinate, if I normalize by the length scale in the outer region which is somewhere here, it is going to be a small region. Okay. So you have what you call Prandtl's matching principle. We are insisting that in the overlap region both the approximations are good. Okay, so you can either take this function or you can take this function, and we are going to equate these two functions in the limit as RE goes to infinity. Now, as a first cat, you will see that this value is going to be small because this is nothing but yp star. Okay, the y star for a point which is in the intermediate region, and this quantity is capital Yp for the same point. So this quantity is large. So we will have u inner of x star comma infinity is u outer of x comma 0. This is what was suggested by Prandtl. Or you can write it this way: as y goes to infinity, the u inner solution must approach, must be equal to limit, or there are different ways of writing it. This I will write as u outer of x comma 0, or another way to writing it is that limit y goes to infinity, u inner x comma y is limit u outer x comma 0 as y goes to 0. Now what is this quantity? This quantity is the u outer is the solution of the Euler's equation in the outer region, which you are now evaluating at the wall, and that will be non-zero because the inviscid flow, the Euler's equation represents the solution for inviscid flow which will slip along the wall. So that need not be 0. So this is some function which you can call, say, u0 of x. So now what we can do is go back and make the summary that you have rho u del u del x plus v del u del y is equal to minus dp dx plus mu delta u del y square as the approximate equation in dimensional form. So this represents approximate balance of x momentum, and you have the continuity equation. Now you have a second derivative of u with respect to y. So you need two boundary conditions. One is at the wall, at y equal to 0, you enforce the no slip boundary condition u equal to 0. So this was a condition which you could not apply on the solution of the approximate equations in the outer region. That is why you have to supplement the solution by another approximation in the inner region. And the other one is the matching condition. As y upon delta naught goes to infinity, your u approaches what we are calling u0 of x, which is this quantity. Now, we have argued that the boundary is thin, so you may wonder why you are applying a bounding condition in infinity. So if I simply write as y goes to infinity, that will give you a wrong picture because it is not a true infinity. Okay, it is an infinity on the boundary layer scale. So you are just outside the boundary layer, which is physically a small distance from the wall, but it is large compared to the thickness of the boundary layer. So the correct way to write it is as y by delta naught goes to infinity, u goes to u0x. So you have you have a second derivative of u with respect to y, so you have two conditions in the y direction. Now you have a del u del x here. So put one condition at x equal to 0, u will be your u infinity. And here for this flat plate boundary layer, we have found what is u0 of x, that is u infinity. Now you don't need another boundary condition on x at another x location because you don't have the mu delta u del x square term. That is the advantage. Okay. Now if you look at the y gradient, if you look at the v for example, there is no del v del x in this system. So you don't have to put a condition on v at x equal to 0. But you have a del v del y, so you are going to have a condition that y equal to 0, you will set v equal to 0. This is your no penetration condition for an impermeable wall. So you have two conditions at the wall. This is a no slip condition which refers to the tangential component of the velocity. This is the no penetration boundary condition which is on the normal component of the velocity, the component of velocity normal to the wall. You have one matching condition here. Now you cannot apply another boundary condition on v here in this boundary layer model as y goes to infinity because there is no del to v del y square term. You have only a del v del y term. Okay. And at x equal to 0 it is this. So what are the unknowns here? Unknowns are u and v only, and there are two equations. So what is this pressure gradient? This pressure gradient then must somehow be found from some other considerations. Okay. Now what we'll do is, the easiest way to do it is to look, one way is you can match the pressure the same way as you match the x component of velocity, but I'll show you an easier way. You just look at this equation and take the limit of each term as y goes to infinity and use this boundary condition. So what we'll do is, we'll write dp dx as mu delta u del y square of x comma y minus rho u x comma y del u del x x comma y minus rho v of x y del u del y of x comma y. All I have done is move the pressure gradient term to one side of the equation and kept the viscous term, there is only one viscous term, and the two acceleration terms on the other side. Now you see that the viscous term can depend on x and y, this term can depend on x and y, this term can depend on x and y. But if you look at the combination here, that will depend only on x. Okay. Now I can evaluate the right hand side at any y, and if I subtract these two terms from this one, it will become independent of y. That is what this equation is telling us. Now at infinity we know what is y, what is u, sorry. As y by delta naught goes to infinity, you have u approaching, let me call it still u0 of x. Okay. Now that means for y by delta naught large enough, u will always be u0 of x no matter what the y is. So the slope del u del y will go to 0. This is what is called an asymptotic boundary condition. The velocity is asymptotically approaching u0 of x for large values of y. Not only this, the second derivative also will go to 0. So if you look at the right hand side here, for large values of y, first term will be 0, last term will be 0, and this will be u0 of x and this will be du0 dx. So you can say that dp dx is minus rho u0 of x du0 dx. This is coming from this condition. This was the matching condition. So if you want to make a summary, there is another way of writing the modular model. You simply write it as rho u del u del x plus v del u del y is equal to rho u0 du0 dx plus mu delta u del y square. and del u del x plus del v del y equal to 0. So this quantity is known. You have to first solve the Euler's equation in the outer region and find what is u0 of x. Evaluate the slip velocity at the wall, and from that you can find the pressure gradient. So the art of a solution is giving you two conditions for the viscous flow calculation. One is it is telling you what is the velocity at the edge of the boundary layer. It's also telling you what is the pressure gradient inside the boundary layer. We have found that the pressure gradient in the transverse direction is 0, approximately, del P del Y is 0. So the pressure of the outer flow is impressed upon the boundary layer. So you solve the outer flow equations and you can find what is the pressure gradient inside the boundary layer. Pardon? Last step is not clear. Okay, this one. See, u is a function of x and y. This one. Why this is 0? Okay. If you look at, say, del u del y at any x comma x naught y naught, let us say. Okay. What is it? It is limit u of x naught y naught plus delta y minus u of x naught y naught by delta y as delta y goes to 0. That is the definition of this del u del y. Now, if y is very large, then what is this value? This is 0. What is this value? This is also 0. Okay. So del u del y will be 0. So physically, if we plot, say, u of x naught y versus y for a given value of y, if we say this is your u infinity and this is the origin 0 0, you are going to have a profile which is like this. There will be a sharp gradient, and then it is asymptotically going to u infinity from below. So you see in this region, the slope del u del y is 0, the curvature del 2u del y square is 0, and so on, all higher derivatives of 0. So it will become u infinity only at infinite distances from the wall, according to this model. Okay. And if you want to define a modular thickness, you can define it as the distance from the wall where the velocity is, say, 99% of the free stream value. So if I say this one is 0.99 u infinity, then this is what I will call delta x. So for all practical purposes, when you are at a distance delta x from the wall, you have reached infinity, but strictly speaking, you are reaching infinity only at infinite distance, reaching u equal to u infinity only at infinite distances. Is it clear? Okay. All right. Now, for the flat plate boundary layer, and we have also considered the case where the plate is aligned with the direction of the flow. If I incline this plate, the whole thing will change. Okay. So we are considering a plate which is aligned with the direction of the stream flow. So here we have found that u0x is u infinity, a uniform profile. So du0 dx is 0. That means this is a dp dx equal to 0. So this is what is called a zero pressure gradient boundary layer. So for the flat plate, this term is going to be 0. But there you are going to have boundary layer flows where this could be plus or minus. Okay. And maybe in the main workshop we can talk about what is called favorable pressure gradient and adverse pressure gradient, and we will show that when you have an adverse pressure gradient, there is a possibility of having a reverse flow near the wall, which is called boundary layer separation. Okay. But to understand why there is an adverse pressure gradient, it is very important for you to understand this matching principle. If you don't understand the matching principle, then you cannot explain why there is an adverse pressure gradient under certain conditions, why there is a favorable pressure gradient under certain conditions. Okay. And why the pressure gradient is 0 for this condition. So I think I will stop here.